So last time we started talking about these large language or actually language models. When they're not large. But the basic idea was you would model the text as a sequence of tokens. And in particular, we're going to focus on a certain chunk of text, which you can call it either a block or a context. Usually they call it context. Let's say this is of length t plus 1, so token 0, token 1 of the token t minus 1. And then we have token t. So the idea is that we want to predict the next token. So let's say this is my context. This is the target. So we want to, given the context of t tokens, the first, like from 0 to t minus 1, we're going to predict t. And so we can model this as a sort of a Markov process where you have, you want to model the joint distribution. If I model the joint distribution, we talked about the idea that this is an example prediction problem with discrete features and discrete target or basically multi-class classification. So I want to classify or predict this, which has, like, let's say, C classes, C being the vocabulary size. So the examples that we had, we have t equal to 8. The context is 8, C is 64. So let's say you're tokenizing the little letters in the alphabet. So I can put 226, what's wrong? 26 lowercase, 26 uppercase, and a bunch of punctuation. So 64 is a good 64, 65 is a good size. This is the English language. And so each one of these words will have this 64 levels. And we call them words, but they're really tokens. And so it could be like a punctuation mark here. It could be like a space here. There's space in particular, and maybe
go ahead.
Maybe I don't name it, but the character that causes you to go to the next line, /n. Okay, character. So that's also part of the tokens, and it's important if you want to have a well-formatted text. You don't want to have just a bunch of characters stringed together. You need spaces and punctuation marks, including going to the next line, which is very important for things to look like language. And okay, so what we do is we model this problem as a classification problem where you have these features and you want to predict this word. So each one of them has a 64 level, and you have t of them, so you get 64 to the t possible combinations. Okay, so 64 to the t possible combinations, and then I have 64 for the response. So we can go to chapter 1 and then try to model this by or approximately, let's say, the Bayes optimal rule, by calculating the frequencies of observation. So we have like the joint distribution between these, which would have it like in total would be like c to the t plus 1 possible combinations, but for each one I'm going to record the frequencies of the particular string that I observe in data, and that would give me a joint probability distribution, and then I can calculate the posterior probability events given these. And then from that I have okay, so you produce like the maximum in posterior, so the probability that this given the previous one, to maximize it, for a given observed sequence, and then the token that expresses the probability is the optimal one. But this would be very costly. So in our case, we did some calculation, I believe. So 64 to the 8 would be 2 to the 48, and let's say plus 1 would be 2 to the 49. And this is big, okay? So
Like that's calculating all the different with probabilities of
all the different combinations that you can get here.
at 0, 1, 2, up to 8.
Up to yes, actually it's 8 plus 1 because right. So this is calculating how many possible so this part is 8. Okay, so we really like this is the context, and we have one more word which we want to predict. So if you want to join, so this is like a marginal distribution of this. Takes this in at the sorry. This part takes this many values. Okay, and if we want to consider this, it would be like 8 plus 1.
Like going back to chapter 1 where we had this tree,
Yes.
survive or not, or male, female. Like we have to do.
So yeah, so you have to do so in chapter 1 it was like so let's say I had like this is actually the bigram model. So let's say you have t minus 1. I just want to predict based on this guy and this guy. Okay, so I want to predict based on so let me go start a new to remind you we're discussing. So I want to predict the next word. So this okay, let's say this based on let's say okay, let's say t is just 1. Okay, so we have w0 up to wt minus 1, which is w0, and then I have w1. I want to predict this, so I'm going to look at this joint distribution, and from this I can get the probability of w1 given w0. Okay, so this would be like the probability of w1 given the w0 w1 divided by the probability of w0. Right. So yeah.
When you said W0, comma W1, the order matters, right?
Yeah, so in this problem, this is the one that we predict. This is like X, this is Y. Right. So, sorry, this is the one that we're going to predict based on. This is the. So when you write joint distributions, the order matters, yes. Right. So this is the first word in the sequence. This is the second word. I want to predict the first word given like the first word given the 0th word. Okay, W1 given the W0.
Yeah, so when we write W0, comma W1, it is the sequence W0, W1, not the property of W0 and W.
I'm not sure what you're talking about this one.
Yeah.
Is it something wrong?
No, I'm saying that W0, W1, the order matters.
Right.
The order would not separate.
No, the order matters here as well. Right, so whenever you have to random variable the probability of X and Y, this is, when I write it, I mean the joint distribution of X and Y. This joint distribution of X and Y is not necessarily the same as Y and X. Right, so they're not necessarily exchangeable. What I'm saying is like, okay, so you have the chunk of text. The first word is W0, the second word is W1, and if you look at this pair, the random variables, they have a joint distribution. Okay, so that's the joint distribution, there's a marginal distribution, which you can read from the joint distribution and you can form this conditional probability, right? And so this is chapter 1. So the chapter 1 was like, I had like binary words. So this is like sex, like female, male, and this is just 0, 1. Okay, so if I want to predict the text that has like F, M in the first word, and then the next one would be 0, 1. That would be binary classification with you. So here is a little more complicated. So here I have 64 here and 64 here. So if you really want to write down a decision tree, the possibilities are more than, so it wouldn't be binary. Okay, so it's a little bit tricky to write the decision tree for this. But in principle, you can calculate these probabilities from the data. Okay, so what fraction? So I'll observe, for example, all the possible cases. So A for the first one, and B for the second one, A for the first one and A for the second one, A for the first one, and let's say this character for the second one. So you have a table of 64 by 64, and then you count how many cases you observe divided by the total number of pairs, basically. So let's say you have the length of the text is n, so there are roughly n choose 2 possible pairs of this form. Oh, okay, so we're going to treat. So this idea is that you're going to treat the distribution of this as the same as the distribution of any other pair. So we're going to treat this as, so this, the distribution of this guy, we're going to treat as the same as the distribution. This guy. So this we talked about before. The text is not like IID examples, but any pair. So let's say I want to predict this one. I'm going to treat all possible pairs as equivalent, sort of, even if they're overlapped. Okay, I treat this as all having the same distribution and independent. If you treat them as IID, even if they're not IID, actually, at least they're have the same kind of distribution, then you can approximate by averages. Okay? So that's actually the bigram model. So that's where I wanted to go, and we talked about last time. So the more general model here is that if you do a factorization, the probability of the first word or the zeroth word, and probably the first word given the zeroth word, probably the second word given the first and the zeroth word, and so on. If you assume that all these probabilities, so this is the perfect factorization for joint distribution. If I treat these basically as Markov, like impose a Markov condition, given the previous word, the rest of the words do not matter. So here, given this one, all the other ones are independent of this. So I can drop them. And so this would be the probability of WP even WP minus 1. And then I'm going to also treat, so this probability really, as I mentioned, potentially depends on, I want to be precise, this potentially depends on T and the location in the context. So maybe like the probability of W1 and W0, the difference, like slightly different than W2 to W1. Okay. So in the middle of the word, maybe. So if you want to be precise, if you want to be more general, even if you do the Markov assumption, this the conditional distribution would depend on T. But if I also assume that it doesn't depend on T, then this is going to be like just a constant probability, a constant table. For every T, it's going to be the same. So this is really a homogeneous Markov chain, homogeneous because this conditional or transition problems, you can transition problems. If I have word x at t minus 1, what is the chance I observe word y as the next step? So imposing a Markov chain assumption and homogeneity, I get this so-called bigram model because this probability entirely can be written as a product that means let's say bigram probability. This is not a bigram, but like conditional. So bigram would be this these joints. So these are the frequencies would be maybe the joint, so the joint distribution of this would be the same. So basically, probability of WT minus 1 and WT is not going to depend on T. Okay. In any case, so I hope this is clear. So we talked about this before. Last time. So bigram model is clear. So we impose this assumption. And once we assume this, so this for a chunk of text, it's simplified. Okay, so I just have a parameter which I can start to estimate. And you can also try to estimate this directly from data, right? You don't have to perform joint distribution, so you go for every, you know how to do this, right? So go for every word. You see how many times different words appear after. So for example, I'll predict, I want to estimate the probability of WT equal A, given that WT, or sorry, say this, the next word, let's say. I'm gonna put a dot here, given that this is A. I'm gonna look at the data, every place that I have an A, I look after it. And I just record like the frequencies of the words that they see after A, and then we do estimate. We don't need the joint to directly estimate this. So all of this we have done in chapter 1, if you remember. So that would be the empirical estimates. If I have the empirical estimates, then I can also predict. So once I have these estimates, you give me a chunk of text, and I look at the pre-design word, and then I look at my probability for this model. So the last word here, and I have like a problem distribution of the next word, and I sample from that problem distribution. So using that plugin idea, we can do this. What we discussed last time was a little bit different. Anyone remembers how we did it last time? It wasn't using like these empirical probabilities directly. How did we do it last time? So use the ERM framework. So we set it up as an optimization problem rather than the counting problem. How did we do that? Sorry?
Like you.
Yeah, so we recognize that this, we can think of this as a parameter. Okay, so this entire thing is a probability. So a matrix, each row of it is a probability. I'm going to think of this as a matrix. And WT minus 1 is going to index into this matrix as the index of the rows. So I'm going to have WT minus 1. I'm going to look at that particular row, and I'm going to read the probability. So each row is the probability of the next one. Okay, so this conditional probability object can be compacted as a matrix. So there is this index which indexes the rows, and this one which indexes the columns. Okay, so there is a compact representation of this entire model as this single parameter. Okay. And then instead of modeling as a probability matrix, we model it as a logic matrix. Okay, so I'm going to have this parameter theta that I pass each row. I pass through the softmax, and now I get the probability vector. So the advantage is, so this is basically the thing that we did in softmax. So instead of working with probabilities, which are not easy to work with, so they have to sum to 1 and they're non-negative. I'm going to work with like linear real vector. And so any real vector, value vector, let's say RC can be turned into a probability vector by applying softmax. So instead of modeling the probability matrix, I'm going to model the parameter as a logic matrix and then apply softmax. Okay. So once I have this, then I can write down a likelihood for the model. Okay, so
by logic metrics again.
So it's a generalization of the logic. So what's a logic in this general sense is whatever vector that goes into softmax and gives you probability. So logic used to be,
But it's not the probabilities that we were discussing before.
no, it's a probability. So logic would be, so remember the binary classification, right? So in binary classification, the logistic regression, we have something like, right? So the probability of y given y equal 1 given x is the sigma of theta x. If I write it as a probability vector, I would have also probability of y equals 0. Given x is equal to x, this is 1 minus sigma theta transpose x. Right, so this is a probability vector. So let's call this maybe P0. And this P1. Okay, so what is the log odds or logit? In this case, it would be log, let's say P1 divided 1 minus P1. And this is the log odds. And I'm gonna, so this in this case would be theta transpose X. We apply the logic to this. That's the inverse of the this log. So sigma inverse T would be log. It's actually P. So you have to review this part. So this is called logic, the log odds function. This is the sigmoid function. And so if I do that, I get that. Instead, I'm going to look at log. So what I want to look at. Okay, so let's maybe look at this one as well. I think I have to look at this probably. So this is what usually people call logit. So what you have here is like something that when I apply sigma to it would give me the probability. So the more general case that we looked at, it's a little bit harder to write. But if you remember the softmax regression, we write it as y equal, let's say y given x is equal to x would be softmax theta x. So we call this thing inside the softmax logit. Okay, it's whatever goes in, and then when I apply softmax, give me these probabilities. It doesn't, the name doesn't matter. Okay, so the concept matters, right? So you have, I give you a vector, let's say. So this will be more confusing because we don't have an x here. So here, let's say I give you a vector. I give you a vector alpha 0 up to alpha. Let's say T, I want to make a probability matrix out of it, or probability vector out of it. You form this divided by the sum of every element. Okay. By the sum, and then e to the alpha 1 by the sum. Okay. So this is going to be a probability vector. So whatever is here, we're going to call it line. Okay. This is sort of clear. It's like the inverse of the softmax, but softmax is not inverted.
So in the GPT example, the vector of alphas you just wrote would be.
This would be the theta I star. It's like the ith row. Each row separately goes through the star. So this theta is a matrix. One row is a vector. I apply the softmax to it. I get a problem with it. Right? Yes.
The entries of that row is frequencies or probability?
This row.
Yeah.
Yeah, what's in there?
What's in there? A real vector, which we call logits, neither probability nor frequency.
How do you get that?
Like, can you construct one of the cells for us? I think.
I can show you in the code. It's just so you have to understand. So let's say, for example, if you have a probability, so you have to go back to the lecture that we did on softmax regression. So so let's say I have like C is equal to 3. Okay, so I want to create a probability vector. Let's say I want to create like 1/2, 1/2, 0. Okay. So how do I create this? I can apply softmax to any vector that you like, which is, I don't know, let's say 5.1, 5.1, and negative infinity. So if you apply softmax to this, you get e to this, e to this, e to this, e to this, which would be 0 divided by the sum. You get 1/2, 0. Does that sound good?
This I understand, but.
It could also, sorry, it could be minus as well. This also would give you the same thing. It could be like 3.78. So that's the issue with them. Softmax is not unique, but any sort of these sets of real numbers that once you do the softmax, you can probably.
This I totally follow. I'm just trying to wonder like the 5.1, 5.1 infinity. Where do those numbers come from in the context of this token word embedding? Like,
So, okay, so this is, I'm trying to parameterize at this point, okay? So in the end, there is gonna be a probability matrix. So this model, when you fit to the data, this is gonna be a probability matrix. Instead of trying to model the probability matrix, I model the data. When I fit the model, this is gonna change so that the resulting P matches the probabilities observed in the data. Okay, so it's a reparameterization of the model.
Yeah, but what you extract from the data will be the P matrix, right? You won't see the logic matrix, just the P matrix. In the data.
Can I say that again?
You
what
won't observe the logic matrix, just the P matrix.
What do you mean you don't observe? You just observe words, right?
Yeah, but
I can extract information about the P by calculating.
yeah, just about the P, not the.
But there's a process to get, right? I don't observe the probability. I just observe the text.
Yeah, but you do the estimation with the counting the words and stuff.
Yeah.
You get the
The
to
P.
the P, not the logic.
I don't want to answer that as yes, because there's a process to get to this. I can have a process to get to that. That's exactly the process that I'm gonna like do. So I'm gonna write down the likelihood based on theta and do the gradient descent on it, and I'm gonna get theta. But it's any like these are all sort of inferences from data, right? And this is a parameter in terms of P, and I'm gonna parameter in terms of theta. So I have a model equivalently like this is equivalent to this, so there's no loss of information here, right? Instead of writing the model in terms of each probability, I'm writing it in terms of data via this deterministic transformation. Okay, so now everything is in terms of the data, I can optimize or so I can read data from data and find gradients. If you think about like different, like counting is one sort of computation, like differentiable optimization is another sort of procedure. Okay, so you get to data using that approach, you get to P using count. But maybe I don't know, 2000 BCE technology, like 1900 technology. So two different. Yeah. Right. Okay. Sounds good. Everyone understands the data. It's not that complicated. It's just the reparameterization is very common. So it's much easier to work with data because I don't have to put restrictions. Like anything goes, like negative, positive, infinity, and I could take small, so the softmax normalizes it and put it in 0 to 1. Right. That's the advantage of using the softmax.
Why are you not taking frequencies as data?
I just mentioned why, because the frequencies have to like sum to, at first I'm not, let's say probabilities, because they have to sum to 1 and they're non-negative, right? Right, and then I'm not, if I just wanted to estimate the P using the empirical averages, then I would be done, yes, I would take frequencies. But I want to build the model. First, this is an interesting way of calculating the frequencies without actually counting. So let's say if I do a bunch of gradient steps, I get an estimate of P without necessarily have to go over counting everything. Does that make sense? It's a better way, better way. So the main idea is modeling this is harder than modeling data. Because then I have to solve the constraint optimization problem. I have to make sure that if I'm trying to write down like a optimization problem in P, I have to put constraints on the rows to sum to 1 and be non-negative. Here I don't do that. It's like an optimization trick. But the thing I mentioned about like frequencies versus this, is also interesting. So this is, this gradually updates the data and, so you can also do it like gradually update P, so you don't have to see the entire text. You have to, you can like have a, like a subsample and then have an estimate and then get more samples updated again. But it's a little more tricky. If I want to gradually update P without saying every pair, every possible pair, you have to think how to combine them. But gradient descent is interesting because you can do like this batch, like mini batch SGD. Do a few steps, you get like a better estimate of theta. Do more, you get a better estimate, and at some point, just things flatten out. So that's enough. Yeah.
So if you're updating without seeing the entire text, I guess the complications you talk about is that we may see new pairs and we may have to add them to the model once we see them.
In which approach you talk about the
You
case?
talk about not seeing the entire text and then like updating it.
Yeah, so if you remember the code that I went to, maybe I should go back to it and talk about it. So what we do is, so we break the text into chunks, right? See if I have it here. So you sample these chunks from the text. And actually, in this case, the code is written in anticipation of GPT. So you actually sample the chunks of length 8, but for bigram, you just need pairs. Okay, so you can sample pairs that say t is equal to 2, and then treat them as IID. Okay? And then you write down the likelihood, and then you do gradients. Okay? And the gradient basically, okay, so maybe let me go. So that's all we did last time. So, so we have these chunks. So the superscript I tells you you're looking at the chunk I, the I chunk, and I'm treating them as independent. So when I write down the likelihood, because of the independence assumption, this step is by assumption. So I think I lost that battery here. So the first step is by assumption. This is also called pseudo likelihood, if you remember. So you're treating this as a likelihood, but it's really not calling the likelihood, but you're approximating it as these chunks being IID. So this is my assumption. And the next is the bigram model. So each one of these chunks will probably be factorized as like this Markov process. So once you write this down, you take the negative log likelihood and normalize by the total number, you get this negative log softmax theta, and you look at it very closely compared to what we can softmax. The difference is really across entropy loss between the labels YIP and these logic vectors. Okay, so logic vector in RC goes into the second argument. The label belonging to 0, like 1 to C goes into the first argument, and so you get data as well, like maximum minimization. So this is the empirical risk minimization approach, rather than counting. Okay, and you can see that this is the entire sample that goes in. But I don't need to get the entire sample. I can like have like 10 chunks of things. The thing is, I don't really optimize this entire loss in one step. I do the gradient descent. So you write down the gradient descent, you have like remember you have like theta hat t plus 1. This t is okay, this is different than the other t. So let's call this, I don't know, k plus 1 is theta hat k minus mu, like step size gradient of this entire loss. Let's call this L. This is also capital theta. Let's say data and theta, okay? Data or theta and data, it's better. That's the last approximation in data. So what happens in mini batches? You need I put like a subset of the data here. And the gradient would be, you can see the gradient is just passes through. So instead of the average over all the samples, I get an average over a subset of the data. And so that gives me a noisy gradient, but you have seen hopefully in your work problem that that's not a problem. You just, every time you do one step, you basically subsample like a bunch of data, calculate the gradient, move in that direction. Next time, another batch of data, and you calculate the gradient and move in that direction. This is this idea of mini batch. Use a subsample. This would be mini batch SGD. If you do it with just one sample of the profit, then it's just the usual SGD. Does that make sense? So we don't need the entire data to be able to run our algorithm. Like there's an oracle that gives you like some substitute, let's say a batch of size, I forgot what we use, like 64 maybe. 64 batches of these contexts every time. Yeah.
In the NG video folder,
Right.
where can we find this like ERM style approach implemented?
Okay, so let's go to that maybe. Okay, just give me a sec. Okay, let's go to right. Okay, so there is this, so I haven't added a lot of things here, which you don't see there, but so the NG video folder, so the one, so this is again by Andrei Karpathy. I made some modifications. So I'm going to modify these two. So this is his version of GPT, which hopefully we'll talk about today. This is his version of Bigram. So that's the entire code for the Bigram model. And so this implements that idea. Okay. So and then I have like a Bigram test IPython that you can like walk through. This adapts the same code, but in like a notebook so they can like execute each chunk. So this Bigram test and this Bigram Python is very close. Okay, so that's the implementation. So maybe remind you how it's done. So here you find the or like the input text, a bunch of like batch sizes. Here 32, block size, that's the T, the context. And then we open the text, read it. Okay, so this one I added myself. This is Alice from the Alice Adventures of Alice in Wonderland. You can try that as well. I'm not gonna do it. But his basic text is from Shakespeare, so tiny Shakespeare. So here's like a chunk of text from Shakespeare. And then we train on this. So this part was not going to go over, but this is like encoding and decoding into tokens. Okay, so if you remember, we turn it into basically tokenized. So look at all the possible tokens in the text. So that's this. Vocabulary size would be, I think, 65 here. And this encode decode is like a nice way. So these are lookup tables, character to
Okay,
index.
I found this on the web for basically tokenized look at all the possible tokens in a text.
This is not very intelligent. So encode, decode, okay. You can read this. This is not, this part is not rocket science. So encode hello, for example, W just encodes it into the indices of the vocabulary. So this is the 21st word in the vocabulary, so first 47. The one is like the space. So when it's sorted, the blank is one. And then here you like, what he does is we display the data into training and test, the validation, what it calls validation. So 90% of the data okay, they're making mistakes somewhere. Okay. 90% for validation. So training, which gives you about 1 million tokens and about 100,000 for validation. There's the get batch, which gets batches of the X and Y. So X here would be again, because we talked about this, I'm not going to go into detail. You can figure it out yourself. So you pass it, whether you want it from a training sample or from a validation sample, you pass like this flag. And it gives you the X and Y, so X would be basically 32 by 8, Y would be 32 by 8 as well. 32 is the batch size. So each row would be one batch, 8 is the context size, T. And so each one, like for X, it would be a bunch of tokens, and Y is basically shifted. So below each token, you see the next token and next. Okay, so that's what I want to predict. Up to this part of the text, I want to predict what is below. To this part, up to 1, I want to predict 46, which is the character from that. So this is a nice way of aligning things, because now I can easily just up to any point. This is my target. The target aligns with that. So these are like coding tricks. You don't have to do this. I'll talk about that maybe. And there's some issues, for boundary issues, for example, here. It might have been better. So at this point, for example, I just see this much, but maybe I should have seen all the previous ones. So this way of packaging things has some drawbacks, but it works for simple. And then you have the estimate of the loss, which I'm not going to go through. So in this case, he takes a batch of data, get batch, and then applies the model to X and Y. And the model, like, so in the forward pass, you computes both the largest, that theta matrix, and the loss. Doesn't have a separate loss function. So yeah, it tells you the loss on given the Y. So if you pass it to Y, usually you don't pass the Y to the model because you don't see it, you just want to predict it. But if you pass the Y, it also calculates the loss between what it predicts and the actual labels that you pass to it. And so this was the entire sort of bigram model. So the question asked is, this is the model, so you have the largest, which is this token embedding table. This is token embedding table is like constructed PyTorch. So here in the self, you initialize it, right? Vocab size by vocab size. Each row is going to be the largest for that particular vocabulary word. And that row, after passing through the softmax, gives you the probability. And in the forward pass, it just applies it to the input data. So this index is the index of the basically the X that P constructs. And it would be T by T. So backside by T, once you pass it through this embedding, token table will be P by T by C. So for every pair of indices, you're gonna see, I have some better slides I'm gonna go through next. So instead of going over the code, I realize it's easier, but this is the code, okay? That's the, if you have the question, and then so let me show you the output of this. And then there's this generator, it generates the data. This is rather easy. Let's not worry about it. So once you do the text, you just select the last one. So this is applies self itself to the data that you give it, and it creates the largest, takes the last one because it is the last one, and then applies the softmax, takes the multinomial, and then append the word that it predicts to the previous ones, and then reiterates. Now, like you pass yourself the entire new index, which is the entire text, and then redo it. So you look at the last word. Like that. The last prediction. So this is the sequence of ideas. I predict this, now I concatenate it, and now the data is that. Next time I'm gonna basically look at this context and predict the next one, and then I concatenate it, and then I'm gonna move my context one there. So this is not hard to figure out. We can talk about it if we need it, but I just want to show you what it produces. So this is the model initialized. So initialize the model. And this is the prediction, okay? predicted this. Okay, this is what it predicts without any training. Data is random usually. You have a question?
Yeah, my question was when you concatenate it and then retrain it, if there is an error in the first.
We don't retrain. When you concatenate, this is for prediction. There's no retraining. When you generate, you predict this, and then given this, you predict this, and given this, you predict this for just for prediction.
So here there is no estimation.
There's no estimation now. In generate, there's no estimation. It just applies the model, and if it predicts the wrong horse, so it goes wrong, that's fine. But you also see a bunch of context before it, right? The bigram is gonna make a mistake because once you predict this one wrong, then the next one only depends on the previous one, so it goes completely off the rails. But a more complicated model still sees part of the context before it. But even if I predict this wrong, I still have this, maybe next time I correct this and this wouldn't have that much effect. So if let's say the context is like 100K tokens, like in like a 200K tokens, like find some of the cardinals, then one token is like not gonna affect too much. Any other questions? So that's the initial one, and then this is the learning part, which is I added a bunch of things which are not on the to actually collect the losses, but the actual part of, you can see the actual training happens here. So you just get the batch, apply the model to this batch, you get the losses and the loss, and then you set the optimizer, the gradient to 0. It actually sets it to none, which is also fine. And then loss backward, and then a step. So this is calculate the gradient of the loss of the way through all the parameters, which in this case is that token embedded table. And then one step of the gradient descent, and then back, calculate the performance of the model, the logits. So we really don't need the logits here. Okay, so we could just put the dash here to meet with loss basically. This calculation of loss gives you all the information about the gradient that this is going to use. So this is the entire training. Okay, so this just loops through this multiple times. This you have already seen, except for the set to none, which is a minor issue. You can just drop it and it should be fine. And then if I do this, so it's going to train. You can see the first loss, the loss of first is very high. And then this is after each 300 steps, is just redo this. This is another idea. There are a lot of tricks that are used. So you don't evaluate, you don't calculate the validation loss in every iteration, but in every 300, you evaluate all to avoid like excessive computation. And here you calculate estimate loss function that you wrote does that. Calculates both the training and the test or the validation estimates. And he uses more data because the batch size. So I have an estimate of the loss here, but with a small batch. So he uses a larger batch. If you look at this, there's the eval iterations. So we have like batch size is 32, but eval, maybe define the eval. Yeah, I don't know where I define the eval. Oh yeah, okay. So eval interval is eval iterations is 200. So you average over 200 samples every time to evaluate the loss. So it's a better estimate. In any case, so this is what it does. Goes from something big to something very small, not very small, but you can see like after 300, basically, maybe like 1,000. Sort of this is the training error and this is the validation error, which are very close. Okay, training error, validation error, very close. There's not much overfitting that can happen here, and you can see it here. Okay, let's actually go to the GPT because I wanted to talk about GPT and already next with most of the lecture. But this is the result, and this is the output. So you can see the output. That's the output. Okay, that's what it predicted. So it's a better approximation to the language than the gibberish, but it's still gibberish. Okay, this is another example. Okay, so you can regenerate from this, and I have another example. I think I have the hello here. So I pass it hello and wants it to like complete. So hello and then R and then goes up. You can redo this multiple times. You can see what you get. But it's better than random. You can observe that there's some sentences, there's some words. Okay. This is better than what? Than this. This is really not, this is the initialization. This is after training. Okay. If you stand back like from the curly feet, it looks like text. Okay, if you zoom in, there are some things that you can like add. So like things that depend on like small words that depend on two. Why, like why? The axis. Okay, so that's bigram. Sounds good? Okay, so let's go to actually GPT, which I was hoping to be able to talk about. And that produces a much better output. So let me share this again. So let's see if we can understand. Okay, so these are my slides on GPT. So I'm going to go over, so this is that GPT.py. And I just want you to walk you through to see how it's like built and to show you some performance. We can't train it in class because it requires a powerful GPU and it takes a bit. But even this very simple model, it's not simple, but like smaller model. But you will see. So this is the class, the main class. And the rest, like if you compare the bigram pi and the GPT pi, a lot of things are the same. So batch splitting and estimation of the loss and the generation is almost the same. So I'm not showing you. The only thing is like this is the entire model. So in initialization, you can see there's the we have the token embedding table again, but the meaning here. The meaning here is different, as I'm going to talk about. And then there's a position embedding table. So there's a vocab size. It's still like vocabulary goes in. So each token goes in, and you get it now in embedding. This is not going to be off dimension vocab size because the meaning is not going to be the probability or logic for the next one. It's just a meaning. So we talked about that the probability or the logic. You can think of it as an embedding of the word. It's like a representation of the word in RD. This is a generic like representation or embedding that the model is going to learn and eventually going to produce those probabilities that we want for the next word. So this happens inside. So this is the core thing that the process is over. So vocab size and embedding, and then you have this position embedding table, and you have a sequence of blocks you can see, and then sequential, and then this is a construct in Python. So star applied to the list, it just unpacks the list. Like it's like block. You just pass it separate into the sequential. So it's just a sequential sequence of blocks. So this is my view here. Okay, so you get this. We'll talk about this embedding that passes through a sequence of blocks, and then you have this what he calls LNF. So the layer norm. So a layer normalization layer. And then a linear layer. So layer normalization is, we can talk about this, just a minor issue, like minor thing. So normalizes the output of the layer. And it would have been better if it wasn't there. So it absorbed it into the block. We can talk about that. But just ignore the layer normalization. And then there's this linear. So the idea is that this n embedding, so n embedding in our case, or in his code, is going to be 384. Okay, it doesn't have anything to do with the vocab size, which is about 65. But this is the embedding size for each of our tokens. And then, so it passes through the blocks, they process. So this is each of our data would be T by 384. So each one of the rows you can think of as one token. Okay, so I have the context of T tokens, and I'm going to write it like this because we'll see. So this is T, and this is N embed, which I'm going to also call D. In his code, he calls it C. Unfortunately, C would have been better for the vocab size. But each one is a vector of length 384. Okay, so this would be x1, x2 up to x, or x0, x1 up to xt minus 1. Okay, so I have this table. And what happens is, in fact, what we do is like we have also a batch size here. So this is going to be, I'm going to observe one of these for every batch, but I'm going to ignore the batch. Okay, so we'll observe tensors of size b, t times that dimension. Let's call this C. So this is what the model operates on. But the batch is like 64 or 82. We're going to ignore because it happens on the parallel for every batch. So we're going to ignore the batch. So you really are looking at I'm going to look at one of these matrices. So you have your x0, x1 up to x t minus 1, and each one is a 384 vector. Okay. And so these are representing the tokens. So for example, the actual token in his code, like it's ID x0. These are the index into the vocabulary. So this could be like, for example, A, this could be C, this could be, I don't know. So each one gets an embedding, which is going to be these vector x's. Okay, so this matrix T by 384. And this is what the model operates on. You can see it here. So this x, I'll talk about this. So logs are applied to this x, and then the layer norm, and then the LM head. So LM head is just this linear map. So you have this x passes through these blocks, a bunch of these blocks. So these are the layers. So that's where the deep learning comes in. You just concatenate many of these. And then the layer normalization, and then the linear. So the linear part just is a linear map that maps from 384 back to, let's say, 65, which is our vocab size. So this is the number of classes. So each one of these vectors, I'm gonna translate back into the dimension, which is, so this now looks like our theta. This looks like our theta in the bigram model. I apply softmax to each row when I'm gonna try to predict, which is not here. So it's in the generate part. But if you apply softmax to each row, then you get the probabilities of the next words. Sounds good? Is that sort of clear? This is not this is not that difficult. Okay, but the idea that we moved from so this embedding is now something abstract, and the way it's constructed is like this. So there's this token embedding. So the words go in and picks the embedding for the word, and then the time or the position goes into this position embedding, and it picks another row, and then they sum them to get this x. So this embedding is like a superposition of the embedding for the word and the embedding for the position. So this is a crazy idea because this location I can just encode just whether it's 0, 1, or not, but they're just mapping it to a high dimensional vector. And so this high dimensional vector is going to represent, for example, if this is the vector, just represents that the word that I'm seeing is a position 2 in the sequence. And so it's added here, so that information is inside XT. So XT contains both information about what word we are seeing and where the word is.
Where the word with respect to?
Within the context. Right? So whether it's like, so this T, for example, is like 0 up to T minus 1. Okay, so it's like a sequence. There's a sequence to it. So word 3 is position 3, word 0 is position 0. That position is encoded into the vector. and then add it to the embedding for the token. This is hard to understand, but this is what they did, and you would assume that, okay, I could have done something simpler. Whether that could work, but this is what GPT does. And to understand this takes a bit of thinking.
In the last example you showed, the position was always the last one, right?
No, so each one of these, okay, so let's say, okay, hello. So this is a particular word, okay? So it's like maybe word, I don't know, 31 in the vocabulary and the position is 0. Okay, so this 31 goes into that token embedding table, row 31 picks up something. And this 0 goes into the position embedding at location 0, picks something, and you add these two up. So this word is a position, or maybe it's like L is L after H or not. Maybe it's not ordered, so it's like maybe, I don't know, 25th word in the vocabulary, and the position is 2. Okay, so this goes into, for this one, we're going to go into like position 25 here, pick the vector, and then 2 is going to be position 2 here, so the second row. And pick that. So I'm going to add these two together. It's just a position is an index. Okay, so every word has a content and a position, T. So that T is going to go into this, the corresponding embedding table. So we embed the position and the word. So people went crazy with embedding. So every information we want to embed in the same space. Even the position is a simple. This information in this can be like encoded simply by an index. But the same goes for word. I can say I can embed in. If you imagine this, there are 65 levels. I could have encoded it as I mentioned, like just a pair of numbers. So this has the same information as these two vectors, but I map each one to a vector and then sum them up. That will be my representation of this token at this position. Right? It takes a while to get used to, but it's a very interesting idea. So now I can process on this vector. So this is a vector. In a vector space, I can add, I can multiply, I can pass through linear transformation. I can basically operate on words in positions as objects that I can manipulate. It's not easy to compute with the indices. But here I can, for example, add up 2 words. So I can add word at position 2 to the word at position 3, and I get a new vector that has some information. So the fact that you can process with discrete objects using machinery of linear algebra is a very powerful idea, I would say. This is, I think, the most interesting part of the model, actually, and plus some other part. There's more, like, this part is more complicated in the original paper, but in this one you can see. So there's just token embedding applied to the index. This is the index, these are the words. And then the position embedding is applying to this basically 1 to T. So this is just like for every word there. So let's not dig into the details. I can tell you about the details, but you can figure this out for yourself. This is just exactly that's what I mentioned. So you pass each word at each position through this token embedding table. You select that row, you select that row in this one, and then you add them up. So this X is just the addition. You see, that's the part. And you get that V by P by C, basically. C here is that embedding dimension. Because for every token in every batch, you get 1 embedding. And now we operate on this tensor. So this tensor passes through each block, and at the end, we pass it through a linear transformation to map back to the number of classes. Sounds good so far. We have a little bit more time. So let's dig into one of these blocks. So what is actually, what processing actually happens here? Oh, okay, so this is the output of the bigram model. Okay, so this is one of these blocks. So if you look at it, it's again pretty simple. There's the init function, which initializes the components basically, and the forward pass, which calculates the output. So what exactly it does is what I've represented here. So this vector xt by 384 comes in, and in fact is, as I mentioned, b by t by 3084 or 384. But I'm going to ignore the b part. Just assume that there's one sample that's going to be for simplicity. So what it does is it passes through, and it passes along some calculation and then add it back to itself. So this is what they call residual connection or residual idea or resonance, if you prefer, when they introduce this idea. Then we can work on residuals. Here it's not really residual, but this is a very interesting idea. To have this like main line. So this passes through, as it passes through, every layer performs some operation on it and then adds it back to itself. So this representation gradually carries more and more information. Okay, and because it's a linear space thing driven superposition. So information is not lost. If I add two numbers, I'm going to destroy the information, but if I add two vectors, sort of things are still. So if there are orthogonal spaces, for example, I have something like this, and I add something like this to it, I can still read the coordinates back. Okay, so the linear space has a very interesting property that you can have things in superposition and you can extract information back. So each layer extracts information from that superposition of information, process it, and read it, write it back. It reads it, writes it back, and so it just updates this superposition sort of idea. So what the first one is the main component, which is what we call multi-layer attention, which you might not have time to go through, but next time maybe I'm going to come back and talk about it. I was hoping to be able to talk about the entire thing, but this is one process, and then after that you get a feed forward. So this is, you can see it here. So there's a layer normalization. Again, you can ignore this. Layer normalization applied to X, self-attention applied, and then added back to X. So we're here. And then a layer normalization is applied, and feed forward applied, multi-layer perceptron, and then added back to X. Okay, so that's what it is. And then let me maybe talk about the forward. So the feed forward is very simple. This is one of the things we've seen before. This is a simple neural network, a linear layer, and a reduced layer, which is its point-wise nonlinearity, and another linear layer. This dropout we can talk about, we talked about briefly. This is another thing like layer normalizations for regularization. So maybe we talk about that. This is sort of minor. And then so this is the net, and then you apply the net to X. So this is something like the dense layer that we created before. So it goes from 382. So this operates separately on each one of these tokens to 4 times that. So I don't know what 4 times is, but t times 4 times 384. So increase the dimension and then decrease it back to so 4 times and that and 4 times and that. So this is one of these things that go like this and back. This is multi-layer perceptron feed forward. We have seen this before in one of the previous lectures. So this part is not that crazy. What is interesting is this in the operation that happens here, which we ran out of time. I'm going to post these slides, and next time we'll go over this. And let's see how it goes. Okay, so this is something interesting that goes on, that goes beyond the bigram model. So the tokens are going to have communication, or like you're going to model the entire basically Joint probability distribution. So rather than the bigram model, this entire thing would have a complicated form implicitly. And so all these tokens know about all the other tokens and all the other positions. And so the way that they do it is an interesting idea, which is very close to the local similarity averaging, or like now Daria Watson and stuff. That's why I actually want to talk about it. So next time we're going to come back and then talk about the details, and then that way you learn about the GPT, and we'll see some of the results. Okay, sounds good. Okay, questions? See you next time. Thank you.